Alright, so this video is for the finding the ratio of moles of reactants in a chemical reaction Prelab. A balanced chemical equation gives the mole ratio of reactants and products for chemical reactions. If the formula of all reactants and products are known, it's relatively easy to balance an equation and find out what the mole ratios are. When the formula of the products are not known, experimental measurements must be made to determine their ratios. So pause the video now, make sure that you have this Prelab out in front of you, make sure that you have the Prelab sheet that has this graph right here in front of you as well. I'm going to finish reading the intro right here, and then I'm going to zoom out and I'm going to go through and work through the preliminary laboratory assignment right here, and you can follow along and do it as well. This experiment uses the method called continuous variations to determine the mole ratio of two reactants. Several steps are involved. First, a solution of the reactants are prepared in which the concentrations are known. Second, the solutions are mixed a number of times using different ratios of reactants. Third, some property of the reaction that depends on the amount of products formed or on the amount of reaction that remains is measured. This property may be the color intensity of the reactants and products, the mass of the precipitate that forms, or the volume of gas involved. In this experiment, the change of temperature is the property that will be measured. The reactions are all exothermic, so the heat produced will be directly proportional to this amount of reaction that occurs. Since the experiment is designed so that the volume of the solution is constant for all measurements, the temperature change will also be in proportion to the quantity of the reactants consumed. In the method of continuous variation, the total number of moles of the reactants is constant for the series of measurement. Each measurement is made with a different mole ratio. And the optimum ratio, which is the stoichiometric ratio for the equation, is the one of the greatest amount of reactants formed and the greatest amount of products. Greatest amount of reactants are used up and the greatest amount of product this forms, and then it generates the most heat. Alright, so to be able to determine this, there's a Prelab exercise over here that uses a different quantity that's measured, but it's going to use the same graphical method that you'll use in the lab. And so it says in this one, the following values were obtained in a continuous variations method experiment, and it was designed to find the coefficients in the equation for the reaction between silver nitrate and potassium chromate. One of the products forms a precipitate, and a precipitate is simply a solid that's formed, and then they measured the mass of the solid that forms. And of course, when you have the greatest amount of solid that forms, hopefully that's where the largest amount of each reactant is used up, and both of them limit or are used up. Now we're going to graphically determine this by graphing the grams of precipitate formed on the vertical axis, and then we're going to graph the milliliters of the silver nitrate going from left to right here, and then going the opposite direction, we're going to graph the milliliters of K2CrO4 solution that's used, going from here this direction, getting larger, and we'll match both of those up, graph our grams of precipitate, and then we'll draw some best fitting lines using our straight edge to determine the stoichiometric ratio in the reaction. So the first thing I have to do is kind of get my scale, and I can see that the least grams of precipitate I have is about 1.7, and the most I have is about 10. So just to space this out kind of generally, I'm going to put 10 grams up here, and then I'm going to put 5 grams like right here in the middle, and then I'm going to go all the way down here, and this is going to be 0 grams on this axis. And then my volume, you'll notice, starts at 5 and goes to 45, and then when it adds to the K2CrO4, it's always going to add up to 50, so 45 plus 5 is 50. And so I'll start with 0 milliliters right here of K2CrO4, and I'll go all the way to 50 over here on this side, and I'll go the opposite on the silver nitrate, where I will start with 0 amount of the silver nitrate here, and I will go to 50 at this point. And then I'll plot them oppositely. So first is 5 silver nitrates, so 5 would be about right here. I can put 25 in the middle here to help me space it out a little bit more. And if this is 5 right here, that means this is 45 right here. And at 5 and 45, I get 1.7 grams of precipitate, which would be pretty close to 2, which is right here. So I'm going to get an approximate value right there. My next one is 15 and 35. So if this is 5 and this is 25, this would probably be about 20. 15 would probably be right about here, and 10 would be right here. So this is 15 of the silver nitrate, and that's where 35 of the potassium chromate would be, and that value is 5. So I'm going to take that up right here to 5 and put a dot. My next value is 25 and 25. At 25 and 25, there's equal amounts of these, and that gives me 8.3. So I have to go up here to, let's see, 6. This would probably be about 7.5. So this would be about 8. 8.3 would be right about here. So let's get close to that, approximately right here. And then at 30 and 20, so 30, let's see, 50, spacing it out, this would probably be 40, this would be about 30, so 30 right here, 20 right here, so 30 milliliters of silver nitrate, 20 milliliters of potassium chromate going this way, and that would be about 10, or it lists it as 10, and that would be a dot right up here. And then at 35 and 15, so 35 would be right about here. That would be related to 15 of this. That would give me 9.9. So that gets me really close. It'd be like right up in here, 9.9, super close to right up there. And then my next one is 40 and 10. So 40 would be like right about in here, 10 right about here. And that would get me down to 40 and 10, 6.6. So this would be 6, a little bit higher than that, probably right in this area. And then 45 and 5, so here's 45 and 5 is 3.3, and so here's 2, here's 3, approximately right in here. Now you can see that I'm going to have 2 lines, one starting here and going up to this point, about a best fit, and I'm going to have a second line right here that goes up, getting close to all the dots, but it might not hit every single one of them. And then this point right here, drop that down, and I can get my best or my closest ratio. And it looks like my best ratio would be about 30 to 20, which is about for every 3 silver nitrates, there would be 2 potassium chromates. Are there enough values to make a valid conclusion? Why or why not? Well, you have to have at least 2 dots to make a line, right? 2 points to make a line. And you always kind of want to have one in the middle at least. And it looks like we have at least one in the middle here. It'd probably be nice to have another dot or 2 up in this range, just so I can get the peak a little bit better. And when you do the lab tomorrow, you'll have to decide how many different reactions you want to do and focus on this area right here so you can get the best peak. Now the ratio is different in the lab tomorrow, and you'll have to make your graph as you go along, but that's what this sheet is for on this side right here, where you can make your graph as you go along following these instructions right here. And then this gives you how your graph should be set up. So your assignment today is to finish this graph if you haven't plotted these points, and draw this graph in here, answer these questions down here, and then prepare your graph on this side. And use lots of space on the graph right here, leave lots of room down here, and prepare your milliliters of each of the reactants on the bottom, space it out really nice, and then prepare your delta T over here, which has to be labeled in degrees Celsius as well, just like they do in this graph. So you're all ready to take data tomorrow. All right, good luck on your finding ratios of moles of reactants pre-lab.